All right, strap yourselves in because today we are diving into a real head scratcher. Quantum gravity.
Yeah, it's a doozy.
It's
Yeah.
one of those things that sounds really intimidating, right?
It does.
Quantum gravity.
Yeah,
But we're going to try to break it down, make it fun,
absolutely.
and hopefully you'll come out of this thinking, that was actually really interesting.
And mind-blowing at the same time.
Exactly.
It really is one of those things, everyone's always curious about black holes and the beginning of the universe.
Right.
This is the stuff that gets at all of those questions.
Yeah, it's interesting because we have these two theories in physics that have been incredibly successful, right?
We do.
General relativity, quantum mechanics,
Yeah.
they explain so much of what we observe.
Right.
But when you try to put them together,
Yeah.
it's
Yeah.
like it just doesn't work.
It's like oil and water.
Yeah, like trying to fit a square peg in a round hole.
Exactly.
So we've got general relativity, which is like this big, beautiful, elegant theory
Wonderful. Yeah.
that describes like stars, galaxies, the large-scale structure of the universe.
Exactly. So the big thing.
The big things, yeah.
Yeah.
And then you've got quantum mechanics,
Right.
which is doing amazing things in the realm of the very, very small,
The tiny things.
yeah, the subatomic world.
Yeah.
And they should play nice together,
They should.
but they just don't.
They absolutely should.
So where's the point of, like, where do they clash?
It's really when you get to these extremes.
Okay.
So think like, the center of a black hole.
Okay.
Or like right at the very beginning of the universe.
Right when the Big Bang is happening.
Right.
Yeah.
Exactly.
Yeah.
Tiny space, huge mass, that kind of thing.
And actually, this is something that, our source material, Wikipedia, actually does a great job of highlighting this kind of
It does.
the conflict,
Yeah.
right? In like the definition of what quantum gravity is trying to solve.
Yeah, it's interesting because general relativity thinks of gravity as this smooth, continuous force,
Okay.
right? Like a ramp.
Okay.
But quantum mechanics is like, no. Everything is in these little packets.
It's all chunky, as you said.
It's chunky, yeah, like steps on a staircase.
Okay.
So trying to fit those two together, that's where the big problem is.
Yeah, it's like trying to describe like a smooth, like flowing river,
Right.
but you're using like Lego blocks to do it.
Exactly, yeah.
You can get the general idea, but you're never going to quite get those finer details.
Yeah, and it's not just theoretical, right?
Right.
We need this stuff to understand black holes, to understand the Big Bang.
Right. It's not just a math problem.
No, this is like, how does the universe work?
Exactly.
At the most fundamental level.
Okay, so the stakes are high.
The stakes are very high.
So then how do physicists even begin to tackle this?
Yeah.
Where do you even start?
Well, there are a few ideas floating around.
Okay.
Some of them a little out there.
Out there. Okay.
We're talking about things like string theory,
Okay.
which we'll get to. And that's where things get really wild.
That's a whole other can of worms.
Exactly.
Okay, so we're going to dive into string theory.
Absolutely.
I'm excited.
Let's do it.
But before we do, I want to define this term because I feel like we're going to be saying it a lot. Planck scale. What does that even mean?
Yeah, that's a great point because it comes up all the time. So imagine you're zooming in, right? To the fabric of space-time. Smaller, smaller, smaller.
Like smaller than an atom.
Way smaller.
Okay.
Smaller than anything you can possibly imagine.
Okay.
And you get to this point that's so tiny, it's almost impossible to comprehend.
Right.
We're talking 1.6 by 10, 35 meters.
Okay, so really, really small.
Incredibly small.
Like inconceivably small.
It's the smallest possible distance that makes sense.
Okay.
That's the Planck scale.
And this is where things get really funky, right?
This is where quantum gravity comes into play.
Like this is where those effects are.
That's the idea.
Okay.
It's like trying to read a book.
But the font is so small, you just can't see it.
You need, like, a super powered microscope.
Exactly. We need new physics to even look at it.
Okay. All right, so we've got our metaphorical microscope.
Right.
Let's dive into string theory.
Let's do it.
So string theory, it's kind of a big deal, right? People talk about it being a theory of everything. What's so special about it?
Well, it's definitely ambitious, that's for sure.
Yeah.
I mean, the basic idea is that everything in the universe, all the particles, all the forces, they're not actually made of like little points of stuff, but tiny little vibrating strings.
Okay, like little tiny guitar strings or something.
Yeah, kind of like that.
Okay.
But instead of making music, they make, well, everything.
So the whole universe is like a big symphony.
You could think of it that way, yeah. I like that. That's a cool image.
Yeah.
So how does that help us with this whole quantum gravity problem?
Well, one of the really cool things is that when you start looking at the math,
Okay.
String theory actually predicts a particle that looks a lot like what we'd expect a graviton to be.
Okay, now remind me what a graviton is again.
Right, so like light is carried by photons, right? A graviton is like that, but for gravity.
Okay, so it's like the particle that transmits the force of gravity.
Exactly.
Okay, that makes sense. So string theory is like, hey, I found this graviton thing, and everyone's like, whoa, that could be big.
It could be a huge step towards finally bringing gravity and quantum mechanics together.
Okay, all right, so that's pretty cool.
It is.
But, okay, every time I read about string theory, I get to this one part, and my brain just kind of goes, nope.
Yeah, I know what you mean.
Research dimensions.
Yeah, that one's a bit of a head scratcher.
What is that all about?
So basically, for string theory to work, you need more dimensions than we can see.
More than up, down, left, right, forward, back?
Yeah, more than our usual 3 dimensions of space and 1 of time.
Okay, so where are they?
That's a big question.
Yeah.
They could be curled up really, really small, like way smaller than anything we can see with even our best microscopes.
So, like, hidden dimensions.
Yeah, basically.
Lurking in the fabric of space-time.
Potentially affecting everything that we just haven't been able to detect them directly.
Okay, so that's weird, but it kind of makes sense in a way.
And it gets even weirder.
Oh, no.
Yeah, you see, string theory, it doesn't just allow for extra dimensions, it kind of goes all out. It suggests there might be a huge number of possible universes, something called the string landscape.
Okay, and how many universes are we talking about here?
Try 10,500. That's a 1 with 500 zeros after it.
Okay, that's a lot of universes.
That's a lot of universes.
Right, so that's just mind-blowing.
It really is.
But how do you even begin to test something like that? We can't exactly go hopping between universes.
Not yet, anyway.
Okay, good point.
But even though we can't see these extra dimensions or other universes directly, there might be ways to see their effects.
Okay, so it's like we're looking for clues.
Exactly, like cosmic detective work.
I like it.
So one way to look for clues is to study the very early universe.
Okay.
Like right after the Big Bang. There's this thing called the cosmic microwave background radiation. It's like a faint afterglow of the Big Bang.
Right, I've heard of that.
And it might have patterns imprinted on it by quantum gravity.
Oh, wow. So it's like looking for fingerprints at a crime scene.
Yeah, kind of like that.
And have we found anything?
Well, there was this experiment called Bicea P2.
Okay.
They were looking for a specific pattern that would have been a smoking gun for certain types of quantum gravity.
Okay.
But it turned out to be a false alarm.
Oh, bummer.
Yeah, but that's how science works sometimes.
Right. You try, you learn, you try again.
Exactly. And there are other experiments, too.
Okay, like what?
There's the integral satellite.
Okay.
It's looking for evidence that space-time itself might be grainy at the Planck scale.
Grain?
Yeah. Remember how we were talking about how quantum mechanics says everything is chunky?
Right, right.
Well, that might apply to space-time, too.
Plus, like, the universe is pixelated.
Kind of like that, yeah. So integral is trying to see if that graininess affects how light travels over vast distances.
Was it found anything yet?
Not yet, but even if it doesn't find the specific signal it's looking for, it helps us rule out certain possibilities.
Okay, so it's all about narrowing down the options.
Exactly.
So string theory is out there, but it's not the only idea, right?
Right, there are others.
What about this one? Loop quantum gravity. How's that different?
It's a completely different approach.
Okay, how so?
Well, string theory starts with particles and tries to explain how gravity emerges from their interactions.
Yeah.
Loop quantum gravity kind of goes the other way around.
So it starts with gravity.
It starts with what we know about gravity from general relativity.
Great.
And then tries to make it quantum.
So instead of starting small and going big, it starts big and tries to go small.
Exactly.
Okay. I can see how that would lead to a very different picture.
It does.
So how does it actually work? What's the basic idea?
Well, imagine space-time itself, the fabric of the universe, being made up of these tiny interconnected loops.
Like a chainmail suit for the universe.
That's a great way to put it.
Okay.
And these loops, they can only connect in very specific ways.
Okay.
Which means there's a fundamental limit to how small you can go.
You can't have a piece of space-time smaller than one of these loops.
Exactly.
Wow, that's a pretty radical idea.
It is.
So space-time isn't smooth and continuous after all.
That's the idea.
It's like the universe is made of Legos.
Well, maybe not Legos exactly.
Okay, but it's quantized.
Exactly. It has the smallest possible unit.
So we're saying space-time itself, the very fabric of reality, isn't this smooth, continuous thing like we tend to think it is?
That's what loop quantum gravity is proposing.
It's like the universe is pixelated at the most fundamental level.
It's an interesting way to think about it, yeah.
And that chunkiness, those smallest possible loops, they must have some pretty wild implications, especially when we're talking about things like black holes.
Absolutely, because at the center of a black hole, you have a singularity, right?
Right, where everything collapses into an infinitely dense point, according to general relativity at least.
Exactly. But with loop quantum gravity, you hit this fundamental limit.
Because you can't have a piece of space-time smaller than those loops.
Right, so instead of everything collapsing into an infinitely small point, you get this sort of quantum bounce.
A bounce. So instead of everything being crushed into oblivion, there's like a pushback.
You could think of it that way, yeah.
And where does everything go?
Well, that's where things get really interesting. Some physicists believe this bounce could create a bridge to another region of the universe.
Like a wormhole.
Some people even think it could lead to another universe entirely.
Okay, now you're just messing with me. So black holes might not be the end of everything after all.
They might be more like passages or gateways.
That's mind-blowing. But what about the Big Bang? How does loop quantum gravity change our understanding of the very beginning of the universe?
It suggests a similar kind of bounce might have happened then, too. Instead of the universe starting from an infinitely dense point, it might have contracted down to a certain size, hit that quantum limit from the loops, and then bounced back outwards, creating the expansion we see today.
So instead of a Big Bang, it was more like a big bounce.
Exactly. A much more dynamic picture, isn't it?
That's an understatement. So we've got these two really compelling theories, string theory and loop quantum gravity, both trying to tackle this puzzle of quantum gravity. Which one is right?
That's the million-dollar question, isn't it? The truth is, we don't know yet. Both theories have their own strengths and weaknesses, and both are still being developed. It's really a matter of finding which one, if either, can best explain the universe we observe.
It's like we're at the edge of a new understanding of physics, of reality itself.
And that's what makes this such an exciting time to be thinking about these questions.
Absolutely. Well, we've covered a lot of ground in this deep dive. We've gone from the fundamental clash between general relativity and quantum mechanics to the mind-bending landscapes of string theory and the quantized spacetime of loop quantum gravity. It's enough to make your head spin.
To say the least.
But even though we may not have all the answers yet, one thing's for sure. The quest to understand quantum gravity is pushing the boundaries of our knowledge and leading us to some of the most profound and awe-inspiring ideas about the nature of reality.
And who knows what incredible discoveries await us just around the corner.
Exactly. And on that note, I want to thank you for joining us on this incredible journey into the heart of quantum gravity. It's been a wild ride.
My pleasure. Until next time.